Hello again, physics friends. Today we're going to talk about transverse length contraction and show why it does not exist. In particular, we've talked about length contraction as existing as a requirement in special relativity, in fact. And you might wonder, okay, well, in which directions is the length contraction? Is it all directions, just the direction of motion, and so on? And what we're going to show here is that the contraction is only in the direction of motion, and there's no contraction perpendicular to the direction of motion. Now, this has relevance for many reasons. In part, remember when we talked about the time dilation derivation, and when we compared the distance up and down for a clock at rest in our frame to the path that light takes, the triangular path that light takes, when the clock is moving through our frame, and we argued that the triangular path was longer than the up-down path. But if there's length contraction in all directions, then how do we know, for example, that the height of the light clock isn't smaller than it used to be? In other words, what if the moving clock is shorter in the up-down direction? Then it could be that this triangular path is equal to the up-down path, or perhaps even smaller or shorter than the up-down path. But what we're going to show is that the height of the clock is the same whether it's moving or not, but the width of the clock will change because of the horizontal motion. So we can put away this picture for now, and we'll make a following claim and then show the proof. So the claim is that there's no length contraction transverse to the velocity. In other words, there's no transverse length contraction. And what do we mean by transverse to the velocity? We mean if you're moving, say, left to right, then the up-down lengths are not affected. Only the left-right lengths are affected. And to prove that there's no length contraction in the transverse direction, we're going to use a contradiction. We're going to assume that there is length contraction in the transverse direction, and we're going to show that that leads to a logical contradiction, and therefore we can determine that there is in fact no length contraction in the transverse direction. So our setup for a thought experiment for this derivation of no transverse length contraction is that we're going to have a rocket and a tunnel, and the height of the rocket we're going to call L0, and the diameter of this tunnel we're also going to call L0. They're the same. So in the frame of reference, if both objects are at rest, both the tunnel and the rocket are at rest, then the height of the rocket is equal to the height of the tunnel. Okay? Now, let's see what happens if we let the rocket approach the tunnel. So I'm going to draw the tunnel here, and I'm just going to draw kind of the top and bottom walls of the tunnel. Okay? So we're kind of looking at it in cross-section. Here we have the tunnel at rest. So we're in the tunnel frame. Okay, and we're going to configure things so that the rocket is coming towards the tunnel at high speed. Okay, so the tunnel's at rest, and here comes the rocket at high speed, and we're going to assume, let's assume that there is transverse length contraction. And we're going to show that that assumption is wrong. Okay. So again, we're assuming that there's transverse length contraction, and the whole point of this exercise is to show that that is not true. Okay. So now we have this rocket that's moving to the right at high speed. I'll call it capital V for the speed of the rocket relative to the tunnel. In fact, maybe I'll just write V rocket relative to tunnel, VRT. Okay, and let's assume that the height of the rocket is now smaller because of length contraction, and we'll call that L0 over gamma. Right? That's the contracted length. So this is smaller than L. So what happens then? Well, the rocket fits through, no problem. Okay, so the outcome here is that the rocket fits through. Right? The rocket does not crash into the wall of the tunnel. It goes through the tunnel and emerges on the other side. But what we're going to see next is if we look at the same situation from the rocket frame, we will predict that there's a collision between the tunnel and the rocket. So let's see how that happens. So in the rocket frame now, we have the rocket at rest. So its height is what it used to be. Is the defined height is the rest height, L naught. But now we have the tunnel approaching the rocket, because we're in the rocket frame, at high speed, V tunnel rocket, VTR. And if there's transverse length contraction, which again we're going to show is not the case, but if there were, then the height of the tunnel would be smaller. It would be L naught over gamma. Okay. And so what we predict here for the outcome is that the tunnel will collide with the rocket. Now, in special relativity, there are many things that are relevant, that are relative. In other words, people in different frames can disagree on the coordinates that they assign for spatial and time coordinates for objects, but they do not disagree on whether or not an event happens. So either there is a collision or there is not a collision. A collision is not a relative outcome. So we have a conflict here, okay? Or we have a contradiction here. And the contradiction is either there's a collision or there's not, right? The existence of a collision is not a relative concept. Like either the tunnel gets damaged and the rocket gets damaged and we have to fix it, or it does not. Bent metal and broken concrete is not a relative concept. Okay, so we're in a situation now where if we do the analysis in the tunnel frame, we predict no collision. But if we do the analysis in the rocket frame, we predict a collision, and that's a contradiction. So that must mean that some underlying assumption that we're making is incorrect. And that underlying assumption in this case is that there is transverse length contraction. So in fact, there is no transverse length contraction, and this example can show you why there cannot be transverse length contraction. Okay, so this was just a thought experiment to show that although there is contraction in the direction of motion, in other words, this tunnel is shorter in the rocket frame than it is in the tunnel frame, the directions perpendicular to the motion are not affected. So the height of the rocket should be L naught in all frames, and the height of the tunnel should be L naught in all frames, so that the tunnel will just fit through, the rocket will just fit through the tunnel, and all observers will agree on that outcome. All right, until next time, take care and be well.